Hi, I'm Antonio Sala, and in this video we will discuss the animation code in Matlab. A simplistic one. I mean, we are not doing 3D OpenGL stuff, keep it easy. So we are describing the animation code which animates this spring mass system subject to this differential equation, in which we plugged numerical value for the constant parameters mkb, specified initial position and speed conditions, and gave it to dissolve. So it ended up yielding this expression. So it's this position symbolic variable, the one that we are starting with in our animation code. Here we have it. And this commented line indicates that, of course, we have to run the code I showed, which was analyzed in a previous video, so that this position variable is in the Matlab workspace. The result of the code, of course, is showing this animation, starting at a non-equilibrium situation and going to equilibrium. And the goal of this video is explaining the lines of code that I needed to program this. So let's go. This animation code starts by defining the spring shape in here. We have a set of equally spaced points in the horizontal coordinate, and this is the vertical coordinate of the spring points. So I multiply, center up, center down, center up, center down by 0.8. So I get this center up, center down, center up, and so on until I get the right ends. So left end will be at 0, right end will be at 1. And we will scale and translate the spring to draw it in the position we must do. So this is the spring drawing code. TF is also a variable in the workspace that I used as final time in these time response plots in the previous video. It was 25 seconds. And I will present capital N frames, each frame corresponding to a separation of 0.5 seconds. So if this were real time, this would be prepared to render 20 frames per second. Nevertheless, I don't really know if this is or not a real-time animation. That would be important in a video game. In here, I just want to draw a set of frames to illustrate the movement, and I do not want to ensure that they are drawn exactly at the rate of 20 per second. I don't mind. So, in this for loop is the main frame drawing animation loop. How do we draw each frame? Well, we first clear the figure, deleting the previous frame, and then we evaluate the numerical function pos. This is important. Position with an object of the symbolic toolbox consisting of let's say a string of letters and some numbers, e cos sin. Matlab function compiles it to a numerical function in which I get time as input and I get position as output, as floating point numbers, and not as a sequence of characters writing symbolic expressions. So this Matlab function transforms from symbolic toolbox to ordinary Matlab programming code. Please browse the documentation for further information. So pos is the actual stuff we need to animate. It's a function of time, so I feed this pos function with the actual time for frame I, given in this time range. So P is the position at that time, which just means, computing for that time value of this expression, saying that the result is 1.27. Okay, so once I have this lowercase p, a number, as the position in a given time, then let us proceed with the drawing. This magenta line, here we have it, marks the equilibrium position, 0. The patch command draws a filled polygon. Again, look at the documentation. In here, this line draws this greenish background. And this line here draws this almost black left end. This yline draws this horizontal stuff. And this one draws the other horizontal line. And this draws the spring. How? Well, making a displacement and scaling in the horizontal direction. Spring x goes from 0 to 1, so if I subtract 5, then I move length 1 spring 5 units leftwise, so this minus 5 ends up being this left end of the spring. And as this mass has a width of 2 units, then this is half the width, 1 unit. So this will be the position of the spring, will be P, this will be P minus 1, and P minus 1 is P plus 4 minus 5. So this thing here ends up computing the position of the right end of the spring at the correct value. So this is the way to draw the spring in blue color. This patch command draws the red moving mass. I execute it so that it moved from the equilibrium to the initial position for the animation. And basically, this is a polygon. This is this kind of almost a square that is displaced P units to the right hand side because, okay, this is P, so we move stuff P units to the right hand side. And so this patch command ends up drawing the red moving object at each frame. Again, you can change shape X, shape Y, and look at the documentation of patch to better understand what we are doing here. This xline at position P is this vertical line marking the actual position of the mass. The only remaining things is writing the title, some texts and axes and some font sizes, and this is what it actually draws each frame. And in the first frame, we do pause to freeze this thing at the initial position, which is of course 3, because we solved the differential equations explicitly requiring that. Of course, initial velocity will be 2 meters second to the right. Then we ended the explanation of the whole simulation loop. You can see here. So if now we press F5 and press a key, we end up with this animation that plots the required response, illustrating the meaning of the solution of the differential equations in a possibly better way than just presenting these time response plots. But okay, the data is exactly the same. As a last simulation, we may think in changing the friction coefficients, for instance. If we set 10 times less friction, the system will be less damped and oscillations will take longer to vanish. Indeed, in these 25 seconds, oscillation vanish very little. So if we now run the simulation code, we see how oscillations take longer, and in fact, when it ends after 25 seconds, oscillations will not have stopped. In order to see this stop, we should run this for a longer time, but okay, we don't do it. So this is a very slightly damped simulation. On the other hand, if we increase the damping to say 0.7, oscillations take very little time to vanish. So these sines and cosines are multiplied by a faster decaying exponential. And if we do increase a little bit more to say 1.5, then the system is so damped that there are no longer sinus and cosinus expressions in the solution. This is what's called the overdamped case. And the simulation plots are no longer oscillatory. And of course, the animation will quickly stop without oscillations at the equilibrium position. This is the overdamped response in second order systems. So we'll finish with this, okay? To summarize, in this video, we did show how to compute animations of the mass spring system so that we could get a feel of the intuitive meaning of the solutions that we plot in previous videos, consisting exponential only terms if overdamped, and exponential plus trigonometric functions if underdamped. So we finish here. Thanks for watching.